Um, Thank you very much for the introduction, and sorry for the fiddling with the thing. Can you hear me okay? It's already like the first day and I'm losing my voice. I'm not built for this kind of stuff. Anyway, I'm going to show you many things very, very quickly, and all of this is supposed to just be sort of like teasers of like, hey, like nuggets of information that you can grab onto and then come find us, as the Ligero guy said, come find us and ask us. It's a lot of information, so I hope it's okay. So I'm going to talk about coSNARKs and private shared state. I'm Ash from TACEO. So maybe one thing to start is like, how many people here have heard about coSNARKs already? So 1, 2, 3, 4, 5, 6, 7. Okay, are they the same 10 people that were at the NORCon earlier? Maybe, yeah, this is one. Okay, 2. Well, maybe you'll recognize some of the slides, but then also, do people know about multi-party computation? Okay, it's a ZK Hack Meetup, so I'm not going to ask that, but like for multi-party computation, do you know about this kind of stuff? Yeah, okay, great. Then I can go into the fun stuff quickly. So, one of the things I want to say is that the reason we're here is to talk about private shared state. Okay, we're all coSNARKs this and ZK that and MPC and FHE and TEEs and la la la. Like, let me throw another 3-letter acronym in there, and we're really here to talk about private shared state. And I want to tell you why for a second. So, being ZK people, you will probably be quite familiar with state models and things like this. So you know with Ethereum that you have this public state, this blockchain that everybody can read, everybody can verify, you can build stuff on it, you can build stuff on the stuff that you built, and it has all this nice public verifiability, composability, makes this like new world of development, and it's great. Except it's not great because it's very slow. I just realized it's being recorded, so I better not swear. It's very slow. And so all this ZK stuff came around to help with the scalability side of it. Then when we got the ZK side for scalability, lo and behold, privacy comes in tandem. So then you see things like Aztec, Aleo, Maiden, Midnight coming up, where there are like these ZK chains that give you this state, like different state model now, but around privacy. Does it have composability? Not really, because actually this privacy normally kind of resides locally on your mobile phone or client side or whatever. And so we have this public shared state, this like beautiful vision of Ethereum, and now we have this private stuff where we're very happy, but like we kind of lost all this composability that Ethereum gave us, and we're back to square one. And so what we really want is this sort of new state model where you get the composability of Ethereum, the privacy of something like Aztec, and then you're kind of like, okay, well, what is this now? Some sort of composable private state? Yeah, so we're calling it private shared state. This is the dream that we're going for. The reality means that actually if we want to realize this private shared state stuff, it means that we need to start actually computing on the encrypted data itself. Not client side, not necessarily on an L1, but like somewhere else. We need to do some computing on encrypted data. And so, yeah, this is what will give us the composability. But again, remember, this is not the kind of Web 2 computing on encrypted data. Now we're in the ZK world. We want composability, but we also want verifiability. And so, yeah, this is where coSNARKs come in. So the verifiability is like the classic case of ZK. This, computing on different states without revealing to anyone. This is the classic case of MPC. So there's a question like, if we put the two of these together, does it work? Yes, it does. It's called Collaborative SNARKs. And this came about in 2021 from Dan Bonnet and his PhD student at the time, Alex. They sort of, ported the ZK prover into this MPC setting. This is cool, right? But as Lucas said earlier, I think was a nice analogy, this is like a great blog post, unless you show something kind of special about this. What was the special thing? The special thing was that, like, okay, you have ZK, which has some overhead in the computation that you're doing. You have MPC, which has some overhead. And you kind of feel like, okay, if I do ZK in MPC, these overheads are going to multiply and like just become huge. And they show that actually this is not the case. Actually, when you do ZK in MPC for some kind of special things, some caveats, whatever, there are no overheads. So like you can do MPC as sort of kind of for free. And so that was a paper from 2021. They take a single prover, which takes as input a single witness, outputs a proof, it's verified by a verifier. They split it into this multi-party setting where there are 3 provers, where they take in different shares of witnesses. Then you get this privacy, you get your proof, you get your verifiability, you get everything you dreamed of. So that's what coSNARKs are. So for the other few people outside of those 10, this is like a brief intro to coSNARKs. So we at TACEO very much like these because they give us this private shared state world that we're dreaming of. And so we implement coSNARK stuff, not coSNARK stuff, tools, libraries that you can actually use and if you want to build private shared state applications. How do we do this? Well, first we need to implement a lot of MPC protocols. We do this with, okay, I'm going to skip this, but like, yeah, you get no overhead because there's a lot of kind of linear secret sharing that you can use for the efficiency. The main proof systems that kind of are very friendly for this are Growth 16, Plonk also less friendly, but still pretty good. Mostly these are good for elliptic curve based provers. Writing the circuit. So we heard before that like maybe it's not like ideal that you have to learn some new tool chains, and it's like, okay, well, we're in this kind of niche of a niche where you're talking about doing private computation on multiple inputs from different, like the Ethereum state, okay, we're in this kind of weird world where like, okay, maybe it's okay to actually learn some new tooling. So, but we try to do it in the absolute most developer-friendly way that you possibly can. So we build this coSNARK tooling for Circum or for Noir. So if you know Circum or if you know Noir, you can use this and you're all good. So yeah, this is a QR code that links to the GitHub where you see the coSNARK repo. This will show up again later. So how does this look in practice? And I think this is one of the things, this is like maybe the stuff that's most interesting for the people in this room, because I get the feeling, or I make the assumption at least, that you know a bit about ZK, you kind of heard about coSNARKs maybe, and like from people that know about ZK and that know about coSNARKs, they kind of ask slightly more intelligent questions, let's say, because they're able to sort of start reasoning about this, but you're in this kind of weird setting, so it's also hard to reason about. So let's help you reason. So this is a picture that we showed earlier, and like it's like super small and you cannot tell really anything from this, but I'm just going to point and quickly explain some stuff. So like on the bottom left, you have this Noir program. So this is, let's say, for coNoir, the Noir version of our coSNARK tooling. You just write as a developer your normal Noir program, but if you want to leverage private shared state, if you want to do private proof delegation, you want to do some dark pools, you want to do some computing on encrypted data and have a verifiable result of the computation, whatever you want. You write your Noir program, this goes through, then there are different users, Alice and Bob, let's say, using this program. They put their input into the application, the coNoir part of the application secret shares their data into these encrypted shares that are then sent to this MPC network. And the same happens for Bob. And so this is how like private data from different users ends up on the network. So they kind of do this secret sharing in their local environment, send it to the network. The network, so the three provers or the three nodes in this MPC network, do some computation, output a result, and it goes to this, what is called Charlie in this picture, but just could be another server or like a front end, whatever. So you get this proof as an output, and you get the output of the computation. So this is like very, very, very briefly, very high level. As I said, I'm giving you, like, throwing you tidbits of information that you can latch onto and maybe grab us later to ask questions. So yeah, it's just to highlight that you can take data from different people, secret share it, do some computation in a private way so that Bob doesn't learn Alice's input, Alice doesn't learn Bob's input, but somehow they learn some computation on their joint inputs. Are they actually efficient? Okay, so the goal, like from this Dan Boré paper, was saying like, yeah, okay, there's no overhead. You could do this for free. Question is, can we actually do this for free? And so, yeah, the goal is to generate proofs with like no overhead compared to a single prover. The reality is, okay, again, another like graph with like a super lot of information, but like just so that you can see heights of bars next to others and try to like reason about the efficiency of this stuff. So this one is for coNoir. If you saw Lucas's talk earlier, he went into a bit more details about coNoir. With coNoir, like it's quite feature rich, which means that like it can be quite complicated to do an MPC very briefly. But it also means that like us as a team working on this, like we've just been kind of like working hard to like implement as many features as possible, because if people want to try and run programs in a nice way, they want to use all the features of Noir. So we've just been like, cranking out features rather than spending time on optimizations the next while will be some optimizations, but for now, this is like considered quite unoptimized stuff. And for each, like on the bottom, you see like different kind of experiments that we were doing. So for like dark pools with 10 provers, for generating Poseidon proofs, Merkle trees, all this kind of stuff. On the left of each experiment, you see the experiment run in MPC, and on the right, you see in Noir. And so for all of these, pretty much, you see that like Noir is cheaper, so doing it like just ZK alone is cheaper. Doing it for MPC is a bit more. But as I said, we hope to do some optimizations to get this faster. As I said, coNoir, or Noir in general, is quite feature-rich. It's like a versatile language. Circum, on the other hand, is a bit more restricted, and we have a bit more control over what we are doing there, and we can do a bit more optimization pretty quickly. And so these are the benchmarks for the results on coCircum. And you can see for some stuff, we actually get like the same or cheaper than the ZK in MPC. So if you want to do like MPC, like a private computation in Circum, you can do pretty well with like little overhead over like the ZK with privacy equivalent. So again, just some benchmarks, some pictures to show you like the relative differences between running these things. Have a look, grab us if you have questions. And so looking ahead, basically, really this is just kind of the beginning. Like, I don't know if you have seen, I mean, maybe one of the questions I should ask at the start is like, not anymore, how, like, do you know what coSNARKs are? But rather like, have you seen private shared state in reality? Like, and the answer is kind of not really. I mean, people are not really doing this yet. So this is like super the beginning. And so yeah, it's very fresh, it's emerging. It serves a purpose. Like, there are people who are using this and who need this. Like for dark pools, all the ZK stuff that you want to do, all the stuff that you kind of hope to do, kind of actually needs this computation layer on top. And if you want to do this, maintaining privacy, maintaining the verifiability, maintaining the composability, all these kind of fancy features, you need something like coSNARKs. So yeah, there are many open problems. Trust, there's research problems, developer problems, node running problems, economic problems, network problems, all sorts of stuff. So like, it's a super cool, huge area that's really opening up, and there's like everything to do. So it's really cool. Yeah, let us know if you want to experiment, either as like developer, node provider, researcher, whatever. Yeah, there's everything to do. And yeah, so I guess like for me or us, thinking about private shared state is like talking to somebody about e-commerce in 1990. Like, e-commerce is coming, like you don't believe how good this is, how big this is going to be. And I was like, what is she talking about? For me, it's kind of like this. It's like really, again, the start of the internet. And so for me, yeah, also like when people ask what is the use case of blockchain, this is it. Like, this is where you need the decentralization, where you need the privacy. It's the one thing that Web 2 can't give you, like, because it's inherently centralized. Here, this is the thing, like this is it. For me, at least, I care about privacy. So yeah, that's it basically. We need private shared state, use coSNARKs, talk to us, and thanks.